Hey trig class, we're going to look at section 8.3 trig equations. Here's the different objectives we have in here. Solving an equation with a single trig function. Solving trig equations using this TI calculator. Trig equations that are quadratic in form. Equations in trig form. And fundamental identities. And then graphing. But again, you're going to want to have access to a unit circle. It's going to be invaluable. It's going to be so important for trig equations. All right, how do I know if a particular angle is a solution to a trig equation? So basically, all I'm being asked to do here is take the angle that they're giving me and just replace it into the expression and see if that's true. So what I'm doing here is replacing theta with pi over 6, and so that would mean 2 times the sine pi over 6 minus the square root of 3. So I need to find, again, the sine of pi over 6. This is why the unit circle is so important. The sine of pi over 6. The sine of pi over 6 is the y-coordinate at pi over 6. So at pi over 6, the y-coordinate is a half. So this part would just be a half. So 2 times a half minus the square root of 3. Is that equal to 0? Well, 2 times a half is 1. 1 minus the square root of 3 is not 0. So that is not a solution. I can also verify this with calculator. So 2 sine, I'm just going to type in pi over 6 directly minus the square root of 3. If that's equal to 0, when I hit enter, I'll get 0. And I don't. So I can easily verify with the calculator what I'm seeing on the unit circle and just doing the math by hand. So pi over 6 is not a solution. It also says, what about pi over 3? Well, 2 times the sine of pi over 3, if you go back to our unit circle, there's pi over 3. The sine of pi over 3 is now square root of 3 over 2. So that's going to be 2 times square root of 3 over 2, and now the 2's cancel, and I end up with just the square root of 3 minus the square root of 3. That is equal to 0, so that means that pi over 3 is a solution. All right, I can go back to my calculator, hit second enter, bring back the last thing that I just did. I can replace the 6 with a 3, enter, and see that I do get 0 there. So again, verifying this with the calculator is a definitely a big recommendation that you can verify, but you still need to be able to do work. Okay, so you're gonna have to be able to put some work on a piece of paper to show that you knew that. All right, now we are solving the equation cosine theta equals root 2 over 2. So again, this would be the x-coordinate on the unit circle is square root of 2 over 2. So I'm going to look at the unit circle. All right, I want the x-coordinate to be square root of 2 over 2. There it is. It's square root of 2 over 2. But it's also square root of 2 over 2 there. And in addition to that, this angle right here, 45 degrees or pi over 4 radians, makes the x-coordinate square root of 2 over 2. But if I added 2 pi to that, I would be right back there where the x-coordinate is the square root of 2 over 2. So pi over 4 plus 2 pi is 9 pi over 4. That would be a solution. So would pi over 4 minus 2 pi. That would be negative 7 pi over 4. All right, but so would 7 pi over 4. That's a solution. If I added 2 pi to 7 pi over 4, that would be 15 pi over 4. That would be a solution. If I added 2 pi again, that would be a solution. If I subtracted 2 pi from there and I got negative pi over 4, that would be a solution. So I hope you're understanding it. There's infinitely many solutions to this. So what do? Well, we find any time that it happens on the unit circle. So it happens for those two angles. Those are two completely separate angles where it happens. And we write those, pi over 4, we write the 7 pi over 4, and then we write plus 2 pi times either you can do n, you can do k. I typically just write n and just say n. N is an integer, meaning it's a positive or negative whole number. That's what basically is going to lead us around the circle over and over and over again. 2 pi times n. Or you could say 360. If you wanted to do it in degrees, but we typically solve these with radians. All right, so that's what they're saying here. Our textbook does use K for that, but K, N, anything like that would be fine as long as you showed your work. All right, this is just a procedure that they're suggesting to solve graphically. I'll turn that stat plot off, and I'm going to graph cosine and y1, and what do I want it to be equal to? I want it to be equal to the square root of 2 divided by 2. I'm putting that in y2. And then I'm going to do graph, and let me do actually zoom standard here. Zoom 6 is the standard zoom. Actually, let me do zoom trig. Zoom trig is 7. All right, and I can see that there's infinitely many solutions. So what we end up with is, that's the pi over 4, that's the 7 pi over 4. And then this solution right here is the 7 pi over 4 minus 2 pi. This solution that we're seeing here is the pi over 4 minus 2 pi. And it's just going to keep doing that pattern over and over and over again. All right, we can verify, we can press second calculate, that option right there, and then we want to find phi, the intersection, and we can do the intersection of the first curve, which is that cosine curve. The second curve is that y equals root 2 over 2, and then it wants to know a guess. You're just trying to put your cursor over it when you see guess. Where's the intersection you're trying to find? So there's what it gives me. But again, if I don't recognize that as pi over 4, I won't know. And I am going to expect you to have exact answers for this. So as nice as it is for the calculator to verify things for us, if we can't go through and do it with a unit circle, then we're going to have a hard time finding these exact values. So use your TI to check like it's suggesting here on this PowerPoint slide, but you should be able to do it by hand. All right, we're told to solve this equation, but make sure you're paying attention to this. This is telling us where to solve it. So we don't need to keep going around and around and around the circle when we're bounded to a region. So when we see problems like this, what we're being asked to do is to isolate the trig function. So the trig function here is the sine function. We want to get it by itself. And to do that, we're going to subtract the square root of 2 over and divide by 2. So I'll have 2 sine theta is equal to the negative square root of 2. And then if I divide by 2, I'll have sine theta equals negative square root of 2 over 2. All right, remember sine is the y coordinate on the unit circle. So we want to know where's the y coordinate equal to the square root of 2 over 2 between 0 and 2 pi. Remember 0 here, 2 pi is all the way around. Just one revolution on the unit circle. All right, so I'm looking for the y coordinate to be negative square root of 2. The y coordinates are negative when we're down here below the x-axis. So we're looking down here, and we are at negative square root of 2. Here, the y coordinate is negative square root of 2 over 2, but it also happens over here. So those are my two angles that it happens at between 0 and 2 pi. So that's 5 pi over 4, and again at 7 pi over 4. That unit circle is going to come in really handy here, and you are going to have to make this on your own. So watch that video where I go over how to make your own unit circle. All right, we have another one here where we are solving inside a bounded region. So what we have to be careful here with is sine of 2 theta is equal to this number. So don't worry about the 2 theta right now. It's just whatever is in here has to be equal to the angles that make the y coordinate the positive square root of 3 over 2. So again, y coordinates, right? Positive square root of 3 over 2. That means we're in the upper half of the circle. So there's a positive square root of 3 over 2. There's another one. So we could be right here at pi over 3, or we could be right here at 2 pi over 3. So 2 theta is equal to pi over 3. All right, and again, in general, we could have that 2 pi times k, where we could just kind of go over and over and over again. Or 2 theta could be equal to this one over here, the 2 pi over 3, plus 2 pi times k. But if you notice what's going to happen here, I'm going to divide the left side by 2 to get theta by itself. Because again, we're solving for theta. We want to know the angle. If I divide the left side by 2, I must also divide the right side of these equations by 2. So I'll get theta in both cases. What is theta equal to? It's pi over 3 over 2, which is pi over 6, plus, instead of 2 pi k, the 2's cancel, and I'm left with pi. Now I know this gives me a bounded region, so I don't have to do the plus pi times k in general, but I do need to know how far these things are separated to know how many of these angles live in between 0 and 2 pi, and there's going to be more than one here. All right, same thing here. This is theta equals 2 pi over 3 divided by 2 would be 2 pi over 6. Again, we're just doubling the 3 times 2 is 6. But 2 pi over 6 would reduce to just pi over 3. So that would be pi over 3 plus, and same thing as before, the 2's cancel here. So that leaves us with just pi times k. All right, pi over 6 plus pi is 7 pi over 6. All right, 7 pi over 6 is within one of these. So there's pi over 6, that's one solution. 7 pi over 6 is another. Adding pi again, though, I would go back past 2 pi to that 13 pi over 6. That's bigger than 2 pi. So that's too big, so I don't need that one. So it's pi over 6 and 7 pi over 6 so far. But then the other one, pi over 3, that's a solution. Right, plus pi, again, adding pi would get me back onto this same line. That would be 4 pi over 3. You can also just add 3 pi over 3 to 1 pi over 3, and you get 4 pi over 3. So that's another solution. Adding pi again, though, however, would again take me past 2 pi back to 7 pi over 3, which is too big. So we don't need that one. So it's going to be these four angles: pi over 6, pi over 3, 7 pi over 6, and 4 pi over 3. All right, the PowerPoint is just walking you through using different values for k and showing that these are the only ones, k equals 0 and 1, the only ones that are between 0 and 2 pi. All right, I have another one that has been altered, so we want to make sure that we understand where this happens in general. It's like tangent of what makes the square root of 3. So when I'm thinking about tangent, I always think of it as slope, right? This has a slope of 0. This has an undefined slope. All right, this has a slope of 1. And then there's 2 left. Okay, this is undefined. I'm going to put U and D. This has a slope of 0. This has a slope of 1. Again, sine over cosine. This divided by this, they're the same thing. So there's 2 left. There's square root of 3, and there's the square root of 3 over 3. Well, because tangent is the steepness, the slope, the steeper it is, the higher the slope. So the square root of 3 is obviously going to be bigger than the square root of 3 divided by something. So there are the 5 different values of tangent you see on the unit circle. It's just when you go into different quadrants, sometimes they're negative. Sometimes it's the negative square root of 3 or negative square root of 3 over 3. It just depends on which quadrant you land in. But it's going to be one of those 5 values if you land on any of these key points on the unit circle. So there it is. There's where we land at the square root of 3 here. Right? And because it's slope, anything that's on that same line, which this down here is on that same line, 4 pi over 3, those are the values that make it happen. All right, but you can also see it happens every pi units, because that'll get me right back to that same line since tangent is slope. So whatever is inside a tangent, which is theta minus pi over 3, that has to be equal to pi over 3 plus, instead of 2 pi times k, it's just pi times k. All right, and then 4 pi over 3, that's, again, pi over 3 plus 1 pi would be 4 pi over 3. So I don't need to do a separate one like I do when it's sine and cosine. I would now, let me asterisk that. I would if this was like a 2 right here. If this had some other number, I could potentially have to do all the things that I see on here. But because it is 1 theta, it's not scaled. I don't have to worry about the other time that I see it on the unit circle. All right, so I'm just going to add pi over 3 to isolate theta. So I get pi over 3 plus another pi over 3 is 2 pi over 3 plus pi times k. And you got to think about, wait, why is this working? Well, if I go to 2 pi over 3, let me clear all this off. Again, here are the angles where it happens, right? If I rotate to 2 pi over 3, if I rotate all the way to here, and then I subtract, that's my angle, 2 pi over 3. If I subtract pi over 3, well, pi over 3 is 60 degrees, so 120 minus 60 would land me right here, and that is the value that makes tangent equal to the square root of 3. All right, so that's one place where it happens. It also happens if I add pi to that. So again, adding pi is just staying on the same line, but going to the other quadrant. So that 5 pi over 3. If I subtract pi over 3, which again is 60, it would get me down to 4 pi over 3, where the tangent of this is the square root of 3. So the places where it happens is 2 pi over 3, and then again it happens at 5 pi over 3 in the 4th quadrant. So that is my solution on the unit circle, 0 to 2 pi. All right, this one tells me specifically use the calculator. And the reason why it's telling me to use the calculator is because that is not a special value of tangent. So it's not 1 or square root of 3 or square root of 3 over 3. It is -2. And remember, the range of tangent is all real numbers. There are numbers where we equal -2. It's just not going to be pi over 4 or pi over 3 or 7 pi over 6 or anything on the unit circle. So we need a calculator. Now what we have to remember, if I want to know where tangent's equal to -2, I can do a couple of things. Number one, I could do inverse tangent and just type in the number that I want, and it'll give me a number. But do you recall what it's giving me? So on our unit circle, inverse tangent is only defined in quadrants 1 and 4. Quadrant 1 if we have positive angles and positive slopes, and quadrant 4 if we have negative angles and negative slopes. Remember, it's only defined between negative pi over 2 and positive pi over 2. So where is tangent equal to -2? That's a slope of -2. So like, remember that negative pi over 4 is where it's -1. So -2 is slightly steeper than that. So maybe we're down here somewhere. So this number that it's giving me, this -1.1 number, that's this angle right here. We don't want that. It has to be between 0 and 2 pi. It has to be positive. So what do? Well, like we said in the last example, it will repeat that same slope, that slope of -2, every pi radians. So I add pi radians to this, and I'll get this positive angle right here that has it. And then if I add pi radians again, or 2 pi radians from this negative angle, then I'll get a second positive angle where it happens. So I take my inverse tangent, I add pi to it, that gives me one angle where it happens, and then I add pi again. And since that was the last thing I did, answer plus pi, I can just hit enter again, and it adds pi a second time for me. So there's my 2 times that it happens between 0 and 2 pi. Remember, pi is about 3.14. So 2 pi is about 6.28. So you can see 2 and 5, they're both in that range, 0 to 6.28. But if I added pi again, that's too big. So 2.03, 5.18 roughly are the 2 places that it happens between 0 and 2 pi. I just want you to see that you can do this with the calculator. So I'm going to clear this all out, go back into Y1. I'm going to do the tangent of x. All right, on the next line, I'm just going to do -2, the right-hand side of the equation. All right, and now I'm going to do, let's do zoom trig, zoom 7. So there are all these different values of the tangent function, and then there's the -2. All right, now, if you want to, because it says specifically 0 to 2 pi, I can do my window and make it 0, and then this 2 pi, and then graph. And so any intersection that I see in this window, that one there and that one there, I can find via the second calculate intersect feature, number 5. So there's my first curve is the tangent function, so I'm going to hit enter when I get close. There's the second curve, I'm going to get really close, and then there's my guess. And there's the 2.03 that we're seeing right here. And then I would just have to do it again, second calc, intersect, and just have to kind of click over until you get there. All right, notice it's going to go off the screen above, and then it's going to come right back on the screen from below. So there's one, there's the second, my guess. So there's that 5.17 number. All right, and I know that that's the only ones because I made my viewing window be between 0 and 2 pi. All right, solving trig equations that are quadratic in form does require you to remember the quadratic formula. Once again, this is not going to be something that's provided for you on the midterm, so you need to know the quadratic formula. So it says if I have a quadratic ax squared, so if I have a quadratic ax squared plus bx plus c equal to 0, okay, you got to have it be equal to 0 or you can't use this, then the x coordinates are that expression, minus b plus minus the square root of b squared minus 4ac all over 2a. And you're just going to have to know that. That's how we solve quadratics. So what I think of when I'm doing a problem like this is I think of a squared trig function. Kind of think of it as x. X equals, what is it that's being squared here? So it's the sine function. So that means that x squared is sine squared. So I can change this to be, instead of 4 sine squared minus 1, I can change it to 4 x squared minus 1 equals 0. And that's what we refer to as the difference of squares. So that's 2x minus 1 times 2x plus 1 in its factored form. And the reason why this is so important that we can factor it is we have multiplication equal to 0, which means these things in the parentheses must be 0. So 2x minus 1, if that were to equal to 0, then I could solve by adding 1 divided by 2. I would have x equals a half. Or if this one were equal to 0, subtract 1, divide by 2, I'd have x equals -1/2. All right, but now it comes back to trig. X is sine. So this x is sine, this x is sine. So these equations in their trig form are just the sine function, the y-coordinate on the unit circle, equals 1/2 or -1/2. And so now I'm looking on the unit circle for where there's the y-coordinate. Remember, sine's the y-coordinate, +1/2 or -1/2. And so between 0 and 2 pi, the angles that make that happen are pi/6, 5 pi/6, 7 pi/6, and 11 pi/6. So that's the values of theta that make that original equation true. All right, you could verify this with a TI calculator. Again, you would need to type in the original left-hand side. For the way you write sine squared, though, is kind of weird. Sine in a parentheses, close that, squared. That's 4 sine squared minus 1. And you want to find out where that's equal to 0. You just graph it. This is still that 0 to 2 pi window like I talked about before. And so you would just now find, instead of the intersection between this and 0, you could do the intersection if you just went down here and hit 0. You would do second, calculate the intersection. You could do 5, and the first curve is the sine curve. The second curve is y equals 0. Enter, enter. So there's, again, another decimal approximation. If you recognize it, great. If not, you would need to know the answers and basically use the trace feature and do like 5 pi over 6 and see that is a 0. You could do it that way. But you would need to know the answers or know the decimal approximations of all these values on the unit circle, which would be very time consuming. So again, it's going to pay off a lot if you can get the math down to be able to do this by hand. All right, and then just kind of going through these last examples on the PowerPoint. If we have squared cosines, squared sines, or squared tangents with squared secants, or squared cosecants and squared cotangents, anything in our Pythagorean identities, then we need to switch this, transform this to just one, meaning just cosines or just sines. So in this case, I'm going to use the Pythagorean identity right here and solve it for either sine squared or cosine squared. So in this case, just because the sine squared is kind of by itself, it would be easier just to say sine squared equals 1 minus cosine squared. And then I've transformed this equation to only have cosine squareds. And I've already seen how to solve something similar. It had sines, but I can do the same thing with cosines. Bring the cosine squared over, 4 cosine squared minus 1. Factor that just like we did before. Cosine's a half or a -1/2. And then go to the unit circle and find where is cosine, positive or -1/2. Cosine is the x coordinates. So +1/2, +1/2 for x, -1/2, -1/2 for x. So there are those angles that make it happen on my way around. Pi/3, 2 pi/3, 4 pi/3, and 5 pi/3. And that's the procedure they're using right there. Okay. Again, the unit circle is really important on something like that. All right, on this one, notice what we have here. Sine squared plus cosine squared equals 3. Well, we know that sine squared plus cosine squared equals 1 by the Pythagorean identity. And what we're going to end up with here is there is no real solution. So they're showing you all these steps to come up with it, but you can also adjust right at the very beginning. That's a fundamental identity. They're using it on just one, like transforming sine to cosine squared using that Pythagorean identity, but that's equal to 1. And so this equation would say just 1 equals 3, and that's not true. That's never true. So what they're going on to show you here is there is no solution, but I could have gotten that from the very beginning. So this was into PowerPoint, but the transformation, the substitution that they made was one that could have, it showed us that there was no solution, but it went way out of the way to show us there was no solution. All right, and then graphically, sometimes we just have to approximate because there is no algebraic combination of algebraic and trigonometry that can solve a specific equation. We can use some calculus to solve this, but not just algebra and trig on its own. So what we'd have to do here is solve it via a graph. So I have 5 sine x, make sure you're closing that off, plus x. And then on the other one I have 3. Alright, and I'm going to do zoom 7, zoom trig. I'm going to expand my window. I can see, you can tell by the graph the way it's going down and up higher and up higher. It keeps rising a little bit more and more and more. So it's not going to hit it anymore on the left. But just to make sure that we don't hit it again on the right, I'm going to expand my window a little bit. I'm going to make my x maximum be, now it's 0 to 2 pi, I'm going to make it be 4 pi. Alright, I'm going to make my my y max, sorry, be 10 and graph it again. So you can see those 3 are now the only places that it happens in the window, and I can use the intersect feature, second calc, and go through and find those intersections. So first curve, second curve is that horizontal line. I'm going to go all the way over until it's close to that place I'm looking for. So there's one about 0.52. All right, move over to the second intersection. Just kind of use your right arrow key until you hit it again. So 3.18 and one last time. So there's my third guess. So 0.571. So that's the procedure using a TI calculator, and you can get those approximations to those solutions. Sometimes we just have to use technology to help us.